Alright, so let's start. I'm not sure, do you hear me with the micro? So we're trying the micro again. Right, so today we're starting looking at the Moduli spaces of flat connections. And to define those, we need the following data. So there will be several essential pieces of data that we need to fix. So one of them is an orientable two-dimensional manifold or a surface sigma. In principle, it might have a boundary, so there will be the following data here. On the one hand, there will be genus, we denote by G, and in general, well, the boundary might be empty, or if it's not empty, there will be a union of several copies of a circle. For instance, here we fix R copies, and we can imagine something like this. So there will be several pieces in the boundary, and maybe there are some holes inside. We fix an orientation, and that's our first piece of data that we need.
Is the assumption that it's compact?
Yes. Let's put it here. Compact, orientable two-manifold. So the other piece of data is a connected Lie group, and here we need one more piece of information. So as yesterday, let's denote by the calligraphic G, the Lie algebra of G, and we need G to be quadratic, or sometimes, well, here about terminology, it's not uniform. Sometimes people say quadratic, sometimes people say metric Lie algebra. But the point is that we need an invariant scalar product. Well, here I write it with values in R, but if the Lie algebra is a complex valued, then of course it will take values in C, and so this is an invariant scalar product, and invariance means that the bracket of xy paired with z plus the bracket of y paired with xz is equal to 0. And this is for all x, y, and z and g. Perhaps just to remind you, like one example would be G semi-simple. And in this case, you can take the Killing form. To define this quadratic structure. But actually it's much more general. You can also find solvable examples, or you can find nilpotent examples. Just imagine, take an abelian Lie algebra, and then take an arbitrary scalar product on it. Of course it's going to be invariant, because this invariance condition is empty for an abelian Lie algebra. So there is actually a whole structure theory for quadratic Lie algebras, but we're not going to touch upon it right now. Perhaps some remarks about this this extra structure that we introduce. So if the Lie algebra G is quadratic, so we have this scalar product, and in particular, so this scalar product gives you several things. One of them is a canonical isomorphism between G and G star. So once you have the scalar product, you can identify G with its dual space. Now we know that the dual space is a Poisson manifold, and it contains symplectic leaves, the coadjoint orbits. Now it is convenient to think of those coadjoint orbits as being as sitting inside G. So think of coadjoint orbits being parts of G instead of G star. So the other interesting construction is the so-called Cartan's 3 form on G. So once you have a scalar product, this invariant scalar product, you have canonically a bi-invariant 3 form on G. So let me write it down explicitly. Well, for whatever historic reasons, there is a coefficient here. I always get it wrong. I'm never sure, is it 1/12 or 1/6? So it's a matter of discussion. Sometimes it's even 1/24. So okay, let's try to settle in the middle for 1/12. And here what one does, one takes the, for instance, left invariant Maurer-Cartan form, and one pairs it with a bracket of the left invariant Maurer-Cartan forms. Well, in my bad notation, I can also rewrite it as G minus 1 dg, and here G minus 1 dg bracket G minus 1 dg. In fact, also if you want, you can replace left by right here, and it will still be the same form. So instead, you can write theta right So now one small comment about the exercise sessions. We thought that to make it a bit more efficient, we'll try to choose some smaller number of exercises and concentrate on them, because like in the morning it was a little bit of disarray because probably you didn't know on which ones to concentrate. So I'll choose 2 exercises for this class and 1 special exercise only for people with a physics background. So this will be taken outside the exercise session and they will need to report to me directly. Yeah, you will see. It's amusing. So the first exercise for this class, I want you to work a little bit with this 3-form adder. It will be especially useful for us tomorrow. Today it's not going to play a major role, but tomorrow we need to work with it a lot. So one thing is to show that this form is closed using Maurer-Cartan structure equations. And the other thing is to compute a contraction with the fundamental vector fields for the action of G on itself by conjugation. So H maps G to HGH minus 1. So in fact, the answer is given on the on the problem set number 2. But so I want you to check it. So this this free form is an important object for tomorrow's discussion. Okay. So we fix this data, and now we consider, we define A of sigma G. So the space of connections on the trivial G bundle G cross sigma. So for non-trivial bundles, we'll have some small discussion tomorrow on what to do about them. So this is simply defined as a space of 1 forms with values in the Lie algebra. Well, I should say that here, in principle, we start working with infinite dimensional objects, and properly speaking, one should introduce some topology or maybe prescribe some Sobolev classes where all those objects live. So the strategy for this lecture series will be to completely ignore those subtleties. What is nice, normally the answers do not depend on the analytic details. Of course, if they did depend, then we would have to really care about it. So let's not worry too much about the analytic nature. Now, one piece of notation. You see, there will be some kind of confusion. We have a surface, and we'll have forms on the surface. So there is a de Rham differential on sigma. But also, we're going to work with differential forms on this infinite dimensional space of connections. So it would be nice to use different notation for de Rham differentials in these finite dimensional and infinite dimensional contexts. So for today, I will say that straight D is a de Rham on sigma, and let's say delta will be de Rham on curly A and on other related spaces. Okay, now I'm ready to show you the famous Atiyah-Bott 2 form. So it's a 2 form on this space of connections, and it looks as follows. Well, let me give several. Let me write it in 2 different ways. Here, I'm also never sure about those coefficients. I think it is 1/2, but that's usually difficult to decide. And well, it will be confusing notation. Let me try to explain what it is. So here I have A, which is an element of curly A sigma G. The 2 form I try to write down is a constant coefficient 2 form on this infinite dimensional vector space. Now, well, delta A's are obviously differentials of those A's. Now, what is interesting? Those delta A's are 1 forms both on sigma and on capital A. Right? So in principle, you can think of those objects as of forms on the product of sigma and capital A. Now what happens? So this is a 1 form on sigma, and this is a 1 form on sigma. Here I have the wedge product, and this is a 2 form on sigma. Sigma is an orientable 2 surface, so I can integrate. And that's what I do. I integrate it over sigma, and the result is a 2 form on A. So this is the 2 form on A. Maybe if I try to write it, just to make it a bit more clear, I will rewrite the formula in the same way. So I can identify, at any point, I can identify the tangent space to A with A itself, since it's a vector space, and I can choose 2 tangent vectors, alpha and beta, in this vector space. So then one can ask, what's the value of omega computed on those vectors, alpha and beta, and whatever, up to this 1/2 factor. This is an integral of the product of alpha and beta as elements of G, and the wedge product of the corresponding 1 forms. So the difficulty, so the formula is basically very easy and straightforward, but the difficulty of it is that on the one hand, on the values of those 1 forms, the values are taken in the Lie algebra G. On the values, you are using the scalar product. On the 1 form parts with respect to sigma, you're taking a wedge product and then you integrate. And for the 1 form parts with respect to capital A, you're just taking the wedge product. So you see, so there are three parallel stories which go all together, and in the end, what you get is a 2 form on the space of connections. So that's the meaning of this Atiyah-Bott formula. Now, perhaps one small remark. This formula explains to you why we wanted the 2-dimensional manifolds, 2-dimensional surfaces to start with. 2D this was in order to get a 2 form, right? So if we had a bigger dimension or a smaller dimension, this formula wouldn't match. You wouldn't get a 2 form, or you wouldn't be able to integrate. Something wrong would happen. Okay. So now, what we're going to do, the idea of Atiyah and Bott was as follows. This we consider, we want to make it into a Hamiltonian space in the sense of definitions we had yesterday. So now we have a manifold or whatever space which we can pretend to be symplectic. Admittedly, it's infinite dimensional, so maybe it's not so good, but we can still try. And now we need to choose a group which acts. So what about the group? Let me see. So the group which acts is the gauge group, the group which naturally acts on the spaces, on spaces of connections. So the gauge group. Let's call it sigma G. And this is a group which consists of maps from sigma to G. Again, well, properly speaking, I should tell you something about the topology of this space of maps, but I won't do it at the moment. Right. So perhaps I should say still what is the multiplication. So the multiplication, the product in this group is just a pointwise product. So pointwise product. So for 2 elements, GH of P is simply G of P times h of p. Now, for infinite dimensional Lie groups, it's not guaranteed to have to necessarily be equipped with a Lie algebra, but here it works. So there is a Lie algebra, which is the space of maps from sigma to G, and again it's a pointwise Lie bracket. So for xy of p, this is simply x of p bracket with y of p. Well, now sigma g acts on a of sigma g, and well, here there are some choices of how you can write this formula. So let me give you two writings as usual. So a connection or a g-valued one from A is mapped to a joint g minus 1 of A plus the pullback of theta L under the map G, or as I always advertise for you, the better writing is g minus 1 AG plus g minus 1 dg. And here of course I do pretend that I deal with matrix groups and matrix Lie algebras. So if I think of A's as matrices with values in one forms and G's just maps with values in matrices, so then of course I can write down such an expression. And well, perhaps it's an exercise. Probably we're not gonna look at it in the exercise session. But if you've never seen such an action, it's a good exercise. Check that this is an action. Right, of course, it would be easy to believe that just a conjugation is an action, right? Because a conjugation is what we know to be an action already at the group level. But then there is this funny piece. If you never seen such a piece, then check that this is indeed an action. Now, perhaps it's useful to write down a formula at the Lie algebra level. So at the Lie algebra level, so we take x, an element of sigma g, and we act by the corresponding, we apply the corresponding vector field. I think according to our notations we should denote it by xa. We apply it to the differential delta A. So this formula is basically derived from this formula by differentiation with respect to G at the group unit. And it looks as follows. So this is minus a Lie bracket of x and A. So that's where I differentiate the first term. You see that the minus sign comes from the fact that here g minus 1 stands on the left and g stands on the right. That's why here we have a minus sign. And then plus we get the Ram differential of x, and that's where I differentiate at the group unit the g minus 1 dg term. Right. So now question.
So what do you mean by delta A there?
So delta A, again, right, so A is an element of my vector space, capital A. Now I declared and erased that delta is a de Rham differential on this space, on this vector space. So delta A is the differential of this coordinate function. So I basically want to know this vector field, how does it look like? I'm here writing for you this vector field. at the point capital A. And the value of this vector field, so this is the tangent vector, you can say. So this is an element of omega 1 sigma g, which is identified with the tangent space to A at A. So it's equal to this expression. So you take the Durand differential of the map X, and then you take a bracket. It's of course we should check that they both take values in G, and they're both one forms. Here the one form because of the Durand differential, and because A is a one form. As I say, here, well, the difficulty is a little bit in the bookkeeping. Everything takes values in the Lie algebra, that's 1. These are whatever, 0 or 1 or 2 forms on the surface, that's 2. And they might also be functions or forms on the space of connections, right? So that's the difficulty. You have 3 counts. So you have to keep track of those 3 counts. So question is as follows. So we have A. We have the Atiyah-Bott 2 form. It is acted by sigma g. So the question is, can one add here some moment map such that it becomes sigma g Hamiltonian space? Well, in fact, I'm not completely sure. Since it's a lecture series, I thought we should do some computations, or we should do some proofs in the lecture series. So at least one computation, let's say, at the minimum. And maybe that's the point when I want to make at least one computation. So, in fact, recall that the moment map condition we had yesterday, that was about contracting the 2 form with the fundamental vector field, right? So, well, let's try to do it. We now have the fundamental vector field, and we contracted with a Atiyah-Bott 2 form. Well, the first step is quite easy. I just substituted either at the place of the first delta A or in the place of the second one, and actually the results are the same. That's easy to convince myself. So then the factor 1/2 disappears, and what I get is minus XA plus dx, and then here I keep delta A. Well, now there will be several terms to deal with. First of all, I would like to integrate by parts. So here I have dx, and I want to put it actually on delta A. So the term which will stay outside, so by the Stokes formula, the term which I get outside the integral over sigma, this will be an integral now over the boundary, and here I will have delta A. So maybe what I do? Let me finish with this term, and then we look at the other terms, right? So this is the first element in my answer. So in fact, it will be convenient to write it down in the following way. This is actually equal to delta integral over this sigma, and here it will be the product of x and a. Now, what about the rest of it? Well, let's try to see. So the rest of the answer, well, first of all, I get an integral over sigma minus xa delta a, and then I also get the term which is, so from the integration by parts, and this will be minus integral over sigma x d delta of a. In fact, what I want to do, I want to write them more like in the form of the moment map condition, which means that I want to have delta in front, as here, and then I want to have some pairing between x. Here the pairing is given by this product and integral, so I want to have some pairing with x of something. So I want here an expression of this type. So, well, let me try to make this transformation. So, first of all, with this term, let me rewrite it as integral of sigma, and here let me write it as follows: x, and here a bracket of delta a and a. Here you see what I did. First of all, I shifted a here by the invariance, and then I exchanged delta a and a to get rid of the minus sign. Now here I can switch d and delta, so these are two differentials. Normally, according to the standard notation, they anti-commute. So so I exchange them and I get an extra minus sign. Now let me do the last rewriting. Is it okay? Do you still see it here? Or not so well? Is it better this way? So the final answer is delta, or maybe I write it in a different color as before. So delta integral is sigma x, and here I will have dA plus 1/2 bracket AA. So here 1/2 is just because when we put delta on it, it will hit either the first one or the second one again. So these are the two pieces of the answer. Notice, which is not so bad, that they both are of the same form. So there is a delta in front, and then there is a pairing of x with something. So this something on the boundary piece, that's just our connection A, and here that's a combination that you probably know. So this combination is the curvature of A. Sometimes it's called FA. Is the curvature of A. Perhaps just to remind you, so the curvature transforms very nicely under the gauge transformations. So if we take, let me denote this expression by AG, so the gauge transformation of A by G, so then the curvature is simply transformed by the adjoint action or by conjugation in our notations. Okay. So, right. Now we can perhaps proceed with our first observation, but first let me give you this exercise for the physicists. So no number. So for people with physics background, so let's assume here that sigma has no boundary, so it's a compact surface, no boundary. And let's consider a 3-manifold which is sigma times r. Consider now A is a one form on this 3-manifold with values in G. So it's again a connection on the trivial bundle, but now it takes it's a one form on a bigger manifold, sigma times the real axis. Let's consider the following functional of those connections, and it's given by A product dA plus, interestingly, 1/3 of the bracket of A and A. So this function of the connection on this 3-manifold is called the Chern-Simons functional. So I want to ask you to do two things. So one, so show that early equations for this functional give fa equal to 0. And second, well, why do physicists love the least action principle or variational formulations of the problems? That's because there in one formula you encode many formulas. In particular, normally an action functional on the product of a space-like surface and the time line should give you several things. So the symplectic form, in our case this should be a T-abot. Well, in physics there would be also a Hamiltonian. So here we're supposed to find the Hamiltonian equals 0, and in general we would also find a set of so-called constraints. So those constraints here should be the equations then when restricted to those equal time or c equal constant slices, the curvature should be equal to 0. Okay. So in fact, much of what we set up to now, the space of connections together with its symplectic form and together with the action of the gauge group, it's encoded in this formula. And if people with physics background, they're supposed to be able to extract it from there and tell me how it works. Is it okay? Good. Okay, so now back to to our situation. So now we successfully computed the contraction. What about reduction? So let's try to think about reduction. So first, suppose that there is no boundary. So this sigma is empty. Well, in this case, this part of the formula is not there. There is only this part of the formula. And here we can answer this question. What is this mu? Right? We see that this is a typical formula from the theory of Hamiltonian spaces, right? And the moment map, that's what stands here in this place. So then we know that mu is equal to Fa, and well, here for whatever reasons it takes values in omega 2 of sigma g. Now, well, we can at least formally proceed with the reduction. So we'll choose, remember we need to choose the value psi at which we do reduction, and we choose psi equal to 0. So we consider mu minus 1 of 0, and we should divide it by the action of the gauge group. Now perhaps let's write it down a little bit more explicitly. So these are connections on the surface sigma such that the curvature is equal to 0, so that's why this word flat connections, and it is divided by the equivalence relation. A is equivalent to AG for G in the gauge group, so that's why the moduli space. So these are flat connections on sigma modulo the gauge transformations. So let us give a name for this space. So curly M of sigma G. Well, two remarks about it. So one, M sigma G is symplectic. So formally speaking, we saw it yesterday. Of course, here we are risking a little bit because it's an infinite dimensional construction. We don't quite know whether it's really going to work. But in this case, it does work. So there is the Atiyah-Bott 2 form does induce a 2 form on this space. And this form is symplectic. But one important remark here, and we'll see a little bit more of it tomorrow and perhaps the day after tomorrow. Well, here we divide by this huge infinite dimensional group, so we have some risks that the quotient will not be a nice space. Almost for sure not a manifold, but like at some point we have to discuss what kind of singularities we may introduce here. But at least M sigma G risks to be not smooth. Right. perhaps one small example here. So let's put G equal to the real line. Then of course the Lie algebra G will also be the real line. Now what we're going to get here in this case is A, just the space of one forms. Well, there will be no Lie bracket term here because this Lie algebra is one-dimensional, so it's abelian. So this will be closed one forms. And what will be this relation now? So modular, let me write it this way. So check that in the abelian case, the gauge transformations, this will be just adding an exact form. So in other words, these are closed one forms modular exact forms. Or, by definition, this is just the first cohomology of sigma. Now, what is the two form on this space? So the two form is simply omega of alpha beta. So this, if I think of representatives, just not to change notation, this is just given by the integral of the sigma of the pairing between alpha and beta. Of course, we will be more interested in the non-abelian version. So this abelian version, I just show you just to see how it may work in simple cases. Now, what about?
This is the case where sigma has no boundary, right?
Yes.
What about the back of the function? Should there be a d log g there?
Now, what now I here?
Yeah, isn't it not only modding up by exact but also integral?
Oh, this. Okay, this depends a little bit of whether I take G to be S1 or R. So let me take it to be R. Then I think it's probably correct. Sure, if you take G to be S1, then there will be more stuff here. Right. All right. Well, I'm a bit hesitant to erase this formula. So, what about the case when we have a boundary? In fact, here the situation is more complicated. We're going to look at it in more detail tomorrow, but already now, so let's say this sigma is non-empty. So let me here assume also that G is simply connected, to simplify my life a little bit. And let me introduce let's say, to simplify the situation, let's say there is just one copy of the boundary. So this sigma is equivalent to is isomorphic to S1. Well, so let me introduce a subgroup of the gauge group, which consists of maps from sigma to G, which are equal to 1 on the boundary. So then, well, we can proceed as we did before and proceed with the reduction with respect to this part of the gauge group. So this would give us a space, let me call it N, of sigma g, and so this will be connections with the curvature equals 0 and modular gauge transformations which are equal to identity on the boundary. Well, again, by the same argument, this guy is symplectic. But now we don't quite know, right, what to do with this term, how to proceed. Well, notice that here there is an action of the quotient group sigma g mod sigma naught g. So in fact this sigma naught g is a normal subgroup, and this quotient is isomorphic to the loop group. So these are maps from S1 to G. Well, the good news is that this boundary term, so there are several ways to think about it. One can develop the whole new moment map theory for this term. So this was done by Meinranken and Woodward. So they studied the Hamiltonian actions of the loop group, and then they used it as a moment map term. But for us, perhaps for the purposes of this mini course, it would be easier to say the following. So remember, there are two procedures of reduction, as we learned from Rui's lectures. On the one hand, one can proceed with this complicated reduction. You go to the fiber of the moment map and you divide by the group action. But there is another procedure which is easier. Let's just divide by the group action and get a Poisson manifold instead. So you see, my point is, I don't want to take any fiber of this, so to say, moment map. Let's instead do the following. Define now M sigma g as simply a quotient of N sigma g by Lg. Of course, this is just equal to, again, the moduli space of flat connections. But now look at this step that we're making. We're taking a symplectic space. On this symplectic space we have this nice formula, so this action is a Hamiltonian or is a symplectic action, but we're simply dividing by it. We don't take any fiber of the moment map. So this space is Poisson. So in the case of a closed surface, the construction just on the nose gives you a symplectic space. In the case when the surface has boundary, you can still do it, and the construction gives you a Poisson space. There might be singularities in both cases. Now, I'm not sure, how is it time-wise? Do I still have 5-7 minutes, or is it... What? 5 minutes? Because you see, I wanted to finish this lecture with showing you a little bit of the Poisson structure on this space. Let me at least give it a try. It's a beautiful construction. So what about the Poisson structure? Well, before giving you the Poisson structure, I should tell you something about the functions. Now, one idea of how one can construct functions is as follows. So we need the following data for this construction. So let's choose some closed curve, let's say gamma. Let's perhaps choose even a base point, but the base point will not be very important. So gamma, a nice curve on sigma, and let's choose rho, a map from G to endomorphisms of some vector space V. A finite dimensional representation. So then let's consider the following functions of a connection A, parameterized by gamma and rho. So first we are taking a holonomia of A along the curve gamma, starting from the base point P. So a holonomia is an element of the group G, right? So this is an element of G. So then let's take a representation rho applied to it. So now this becomes a matrix. And now take a trace of it. Well, perhaps an exercise, and this exercise I'll do myself in the beginning of the next class. So show that W is invariant under gauge transformations. So these are nice functions of connections which do not depend on gauge transformations. In fact, it is also independent of this base point P. Now the theorem of Goldman explains how to compute a bracket of two such functions. I'll make some further assumptions about the curves. Well, let me see. Right, this will be one curve. So the curves should intersect transversally. So I take two functions corresponding to two curves, and to simplify my life, I'll choose G to be the group UN, and rho will be the identity representation, which maps UN to the n by n matrices. Right. So then, well, actually the theorem of Goldman gives an answer in a more general context, but in this context, let me tell you what it is. So let me call the first curve alpha and the second curve beta. So alpha of A, beta of A. So this will be the sum over the intersection points of the two curves. And well, here we have only one intersection point, so that's this P. And now it will be sine epsilon alpha beta p. I'll say in a second what it is. And then w alpha star beta p, that's a new curve. And I also say right away what it is. So basically it's going to be a linear combination of the functions corresponding to the same type of curves. Where what is this funny guy? This funny guy means just the following. You start at the intersection point, and then you first go along the curve alpha, and then you go along the curve beta. So that's just it. So start at P, and then first do alpha, and then do beta. Now what is this guy? So these are two R-oriented curves which intersect transversally, and we know which one is the first, which one is the second. So this means that these two curves, they induce an orientation at this point. But we already have a fixed orientation on the surface. So this sign epsilon is comparison of these two orientations. So orientation of alpha intersection beta. So this is a very beautiful formula. And just to finish, so exercise 2 for tomorrow morning. Imagine that we have sigma of genus G. Find as many as possible Goldman functions which commute. So if you succeed, then tomorrow we'll do the dimension count. And if we get enough functions, then following Jeffrey and Weizmann, we'll construct a completely integrable system for the case of G equal U2 or SU2. Right. Okay. I think my time is up. So that was it for today.